Welcome back everyone! So last time we learned what the residues are and how to use them to compute real integrals. Today we are going to unleash their true power and show off a little bit. Indeed, after today you will understand how your professor in Calculus 2 was able to compute really fast, really weird integral without doing any calculation at all. So grab your pen and paper and let's tap into the real power of complex integration. Let's look at this real integral. So doing partial fraction on this would be incredibly tedious and so long. Instead, what we are going to do, we are going to promote our real variable x to our variable z. And we're going to use complex analysis to evaluate this integral in a really smart way. What's the idea? So you have to imagine a contour made of two parts, a straight line segment along the real axis between negative r and r, and a gigantic semicircle connecting the extreme of this segment. Our function is going to be f of z equal to 1 over z to the power 4 plus 1. It's going to have 4 poles, where the denominator is equal to 0. And 2 of them live inside our upper semicircle, and 2 of them outside. As we push r to infinity, the length of the semicircle grows, but the hope is that our function is going to shrink to 0 so fast that the integral on the arc will vanish. It's going to be 0. The only thing left then would be our real integral, which is going to be equal to 2 pi I times the sum of the residue inside of the contour. So let's try to formalize a bit what we're seeing in the video. So we are considering the function 1 over to the power 4 integrated along this gamma r, which is this weird contour, which is this line between minus r and r, and this semicircle on top of it, all oriented counterclockwise. Okay, so our goal is to compute this integral into two ways. So one is using residue. So here we're going to use residue, because this is a closed contour and we can compute it using residue. And on the other hand though, we're going to compute it using contour integral. What does it mean? So we are going to go back basically at the beginning of the semester, we're going to do a contour integration. And the idea is to prove that the integral between negative r and r is going to converge to our real integral, the one we want to compute. And the one up above here, it's going to go to 0 as r goes to infinity. Okay? So we have to put all of this together. So first, the residue calculation. So to compute the residue, we have to identify where the function 1 over 1 plus z to the power 4 has poles. So we have to solve the equation 1 plus z to the power 4 equal to 0. Now I'm going to set z equal to e to the I theta. Why is that? Because now in this way the modulus of z is always 1. And this equation, if there is any solution, z must be of modulus 1. And this means that now negative 1 has to be equal to e to the I for theta, which means that theta can be equal to pi over 2 plus pi over 4, sorry, plus pi over 2 times k. Okay, so this equation can be solved really easy. So where are the solution then? So the solution is going to be z1, which is e to the I pi over 4, z2, which is e to the I 3/4 pi, z3, which is e to the negative I pi over 4, and z4, which is e to the negative I 3/4 pi. And how you compute those? Well, you just plug k equal to 0, 1, 2, and 3. And when k is equal to 0, you're going to get this one. When k is equal to 1, you're going to get this one. When k is equal to 2, actually, you're going to get z4. Sorry for that. And when k is equal to 3, you're going to get z3. Okay? So these are the equation, and these are you find them. The solution, sorry, and these are you find them. Great. So now where are they in our plots? So two of these poles, z1 and z2, are going to be inside here. So specifically here you have z1, and over there you're going to have z2. The others are going to be the complex conjugate, so here's going to be z3, and on the other side z4. And these two, they actually don't matter, so we can just forget about them because they are outside of our contour, okay? So the only two that matter is Z1 and Z2. And since we have 4 different solutions for our equation, this means that our function has 4 polar order 1 at these points, okay? So by the residue theorem, I can do this calculation. So I know now that the integral over gamma r of 1 over 1 plus z to the power 4 dz is equal to 2 pi I times the residue of the function at z1, so 1 over 1 plus z to the power 4, plus the residue at z2 of 1 over 1 plus z to the power 4. Great. So let's compute these two residues right now. To do that, we are going to use the formula that the residue of a function p over q, if q is a polar order 1, is just p of the point divided by the derivative of q at that point. So in this case, the residue at z1 of 1 over 1 plus z to the power 4, we're going to have that our q is the denominator, and our p is just the constant, equal to 1. This means that this is equal to 1 divided by the derivative of 1 plus z to the power 4 evaluated at z1. So this is just 4 z1 to the power 3, which is equal to 1 over 4 times e to the negative 3/4 pi I. Regarding the other point, the residue at z2, we compute in the same way. This is going to be equal to 1 over 4 times e to the negative 9 over 4 pi I, which means that it is equal to 1 over 4 e to the negative pi I over 4, okay? Because e to the negative 2 pi I is equal to 1. Okay, so let's put all of this together. This means that my integral over gamma r of 1 over 1 plus z to the power 4 dz is equal to 2 pi I divided by 4 times the sum of the two residue. So the residue at z2, 1 over 4 is already there, so we have to compute this exponential, which is just the cosine of pi over 4, which is square root of 2 over 2, minus I, the sine of pi over 4, which is the square root of 2 over 2, plus, now we have the cosine of negative 3/4 pi, plus I, the sine of negative 3/4 pi. So in this case, we get minus square root of 2 over 2, minus I, square root of 2 over 2. So the real parts, they do simplifies, which is great. So this is left to be pi I divided by 2 times 2, so minus 2I square root of 2 over 2. 2 and 2 simplifies. I times I is equal to negative 1 times negative 1 is 1. So this is going to be just square root of 2 over 2 pi. Okay? Perfect. So this is the result using residue theory. Now, as r goes to infinity, we can rewrite this integral always over gamma r of 1 plus 1 plus z to the power 4 dz as the sum of two pieces. The integral between negative r and r of 1 plus 1 plus z to the power 4 dz plus the integral over the semicircle, this is cr, of 1 over 1 plus z to the power 4 dz. Okay? Now, these two integrals, both of them depend on r, but we have just proved that their sum is always going to be equal to square root of 2 over 2 pi. So what's the idea now? The idea now is that we are going to take the limit on both sides as r goes to plus infinity, And the right-hand side, though, it will not change, it will always stay the same, while the left-hand side is going to change. And hopefully, this integral is the one that converges to our real integral, and this guy is going to go to 0. Okay? So now the next step is to prove that the limit as r goes to infinity of the integral over CR, so the semicircle, of 1 plus 1 plus z to the power 4, dz goes to 0 as r goes to infinity, is equal to 0, sorry. Great. So how do you do that? We have to do some estimates. So first things first, we are going to rewrite this integral using our polar coordinates. So since we are on a semicircle, I can always parameterize z as the radius of the semicircle times e to the I theta. And now theta is going to be between 0 and pi. So this is the integral between 0 and pi of the differential, so r e to the I theta times I, divided by 1 plus r to the power 4 e to the 4 I theta d theta. Okay? Let's take the absolute value of both of them. So this is equal absolute value, absolute value. And now this guy is going to be less than equal. I can bring the modulus inside. So this one becomes the integral between 0 and pi of r divided by 1 plus the modulus of 1 plus r to the power 4 times e to the 4 I theta d theta, because the modulus of I is 1 and the modulus of e to the I theta is always 1. And this is less than equal than the integral between 0 and pi of r divided by r to the power 4 minus 1 d theta. And now the magic happens, because this guy does not depend on theta anymore, so we can evaluate this integral explicitly as pi times r divided by r to the power 4 minus 1. And now why this is good? Well, because all of this chain of inequality just showed that the integral, the modulus of the integral of my CR on the semicircle, of 1 plus 1 plus z to the power 4 dz, is less than equal than pi r divided by r to the power 4 minus 1. Right? Now, this guy, as r goes to plus infinity, it goes to 0. Right? So this shows, this implies that the integral over CR, so that the limit, sorry, as r goes to plus infinity of the integral over CR of 1 plus 1 plus z to the power 4 dz is equal to 0. Why? Because I can bound this integral, the modulus of this integral, by this object. This object goes to 0, so this has to be the limit. Okay, and now the last step. So let's go back a little bit. So we have seen that this equality holds true for all r. So in particular, it holds true when I take the limit on both sides as r goes to plus infinity. And let's rewrite it. So I'm going to take the limit as r goes to infinity of the integral over CR of 1 over 1 plus z to the power 4 dz plus the integral between negative r and r of 1 plus 1 plus z to the power 4 dz. And this has to be equal to the limit as r goes to infinity of square root of 2 over 2 pi. Okay? Oh, but wait a minute. We have just proved that this integral goes to 0. So this means that the integral between negative infinity, so I'm just substituting infinity with r, to plus infinity, of 1 plus 1 plus z to the power 4 dz is equal to the limit as r goes to plus infinity of this guy. But this is a constant, so it's always equal to itself. So this is square root of 2 over 2 pi. And that's it. And there you have it. Complex analysis makes your real monster look like child's play. That's all I have for you for today. Ciao ciao!